The mole is the simplest unit in which we can express chemically relevant quantities. The world contains a phenomenally large number of real particles. It has been asked how many angels can dance on the head of a pin, but a more interesting question for science is what is the head of a pin? The pin, in human terms, is a very small surface. The point of a pin is small enough to penetrate the skin of a human or other soft tissues. Anyone who has ever done any sewing knows the difficulty involved in trying to thread material through the eye of a needle, and so can appreciate the tiny size of that gap. However, in terms of large areas of science, the size of an eye of a needle, or the head of a pin, or the point of a pin, for that matter, is immense. Many bacteria can fit onto the head of a pin. Many more viruses could fit onto that same area. The nuclei within cells are smaller still, but even these are made of smaller molecules. These molecules are made of even smaller atoms, which in turn are made of electron clouds and nuclei. It is at this atomic scale that we find our relevant size scales. Gases are individual particles at the atomic scale. Helium gas is simply a collection of helium atoms together. Hydrogen gas, even though the atom is simpler than helium, is more complicated as it is a molecule or bound group of atoms in its natural state. It is at this scale that gases become individuals. However, the individual gas molecule is of little use to chemists at the human scale. This is where the work of Avogadro and his contemporaries comes into play. Lots of people did lots of different amounts of work on gases. Many people discovered many different types of gases, and many different people worked on how these gases combine together to form molecules. It was Avogadro who hypothesized that equal volumes of gas contain equal numbers of particles. With gas, these particles can be individual atoms such as helium, or bound molecules such as hydrogen. 1 litre of hydrogen contains as many particles as 1 litre of helium. Half a litre contains half as many particles as 1 litre. At this point, it should be said that working out Avogadro's number in itself requires more physics than we are going to cover. I know it's a bit of a cop-out, but we don't have the physics yet. Once we talked about ideal gas laws, there is a method to work out Avogadro's number involving further experiments to do with millican. But for now, all we'll say is that Avogadro's number is about 6.02 by 10 to the 23 particles. It's a phenomenally huge number. It is given the symbol n with a subscript a. The most useful thing about Avogadro's number is that we can use it to relate extremely large numbers of particles to everyday weights and measures. In a way, instead of dealing with individual eggs, which are okay for humans on everyday baking level, it's like bakers talking about dozens of eggs, which to them, in ordering in stock, is much more useful. To us, we can talk about individual atoms when we're talking about nuclear physics, but in terms of chemistry, the individual atom is useless. So instead of talking about individual eggs, we talk about dozens of eggs. Instead of talking about individual particles, we talk about Avogadro's numbers of particles, or moles of particles. 1 mole of carbon-12 is the same as 12 grams of carbon-12. 1 mole of hydrogen atoms is the same as 1 gram of hydrogen atoms. 1 mole of oxygen-16 is the same as 16 grams of oxygen atoms. However, hydrogen gas and oxygen gas are not simple atoms. They are molecules, H2 and O2. That means their molecular mass is twice their atomic mass, 2 grams and 32 grams respectively. If we know the formula of a molecule, we can also work out its molecular mass from its constituents' atomic molar masses. Sugar, or glucose, has a chemical formula of C6H12O6. That's 6 atoms of carbon combining with 12 atoms of hydrogen and 6 atoms of oxygen to form 1 molecule. If we combine together 6 moles of carbon, 12 moles of hydrogen, and 6 moles of oxygen, we can make 1 mole of glucose. 1 mole of carbon weighs 12 grams, so we need 12 grams of carbon. 1 mole of hydrogen weighs 1 gram, so we need 12 of these moles of hydrogen. and 1 mole of oxygen contains 16 grams. 6 moles of carbon weigh 72 grams. 12 moles of hydrogen weighs 12 grams, and 6 moles of oxygen weighs 96 grams. So 1 mole of glucose will weigh 180 grams.